Hi, Julian here from PopcornFX. In this video I'll show you how to create a simple timer from scratch in PopcornFX version 2. So this will actually be only an excuse to tackle one of the hairiest problems that people have had trouble with, which is what we call discretization. So it's the process of loading and storing values from one frame to the next to do some computations. So this would be trivial in other VFX systems, but in PopcornFX version 2 it's a bit different. So let's first quickly see how to create a timer. So you'll just drop a timer node, set it to auto start, and here you have a timer. So I'll quickly explain what you're looking at here. This is a single particle which is using this template node to draw a value, so here the value of my timer, on screen. So to do that it uses 9 billboards and uses this texture atlas to display the correct digit on each billboard. So if you open that, it's a pretty horrible template that does a whole bunch of computations to display that number. So this is only a debug node, obviously, that I copied from the tutorials package, one of these two effects here that use this template to draw debug text. At some point in the future we plan to add an easier to use debug helper to display debug text, such as what Unreal has, where it draws a single billboard with a nice shader that draws the actual number inside the shader directly. But right now we don't have such a fancy shader in the PopcornFX editor, so yeah, we have to use this dirty hack in the meantime, but it does the job. So we're not going to use that. Instead, we will see how to create it from scratch. And I will also show you in other VFX systems, namely PopcornFX version 1 and UEForce Niagara, how you would do that and how it transposes in the V2 node graph. So let's quickly fire up UE4. Here I have a test effect, so that's just the basic fountain, one of the basic templates that comes with Niagara. So here on this panel you see all the particle storage, so the particle attributes. Here I added a new one that I called accumulator. Here on the particle spawn stage I have a set particles accumulator where I set it to a random float between 0 and 1. I also made a scratch module that I disabled, which does basically the same thing except it's done in nodes. So I compute a random float between 0 and 1 and I assign it to the particles accumulator. Pretty straightforward. And then in the particle update stage I have another graph where I load the particles accumulator and I subtract the engine delta time multiplied by a speed which I arbitrarily set to 0.8, and then I store this back to the particle accumulator. So every frame I will subtract dt times 0.8 from the accumulator, which will make it gradually reach 0. And then in the color scale here I use the accumulator to scale the alpha. So this makes my particles progressively and gradually fade out. Pretty simple. Now in PopcornFX version 1 I have made the same effect, so you can see here in the layer I have the renderers, I have the spawn stage with my spawn script, with the initialization of all the various particle data, and here I have, if you look up there in the node properties panel, I have the list of particle fields, which are exactly the same thing as Niagara's particle attributes there. And I have my accumulator float value, and in the spawn script I initialize it to a rand between 0 and 1, so same thing. And in the evolvers, in the evolver stack, I have the physics node with downwards gravity, and I have an evolve script where I subtract dt times 0.8 from the accumulator every frame. So again, this line here is basically the same thing as my Scratch module there, where I subtract dt times 0.8. And then this is slightly different from Niagara. I reconstruct the color from the previous color, and I force the alpha to be the accumulator, which I saturate, because in V1, if you don't saturate it, the renderer doesn't clamp the alpha, so you'll get funny artifacts with negative alphas. So I saturate it, and there you have it. It's pretty simple. Now in PopcornFX version 2, to do this, I'll show you how to recreate that entire effect from scratch. So I'll start with an empty effect. Here I will create my emitter, set it to infinite to spawn 90 particles per second. I will create the layer, which will be my actual particles. Hit Ctrl R to reset the simulation and have the emitter pulse events there. I'll add a billboard node so I can see my particles. I will pick a texture, wire in a physics. I'll disable the collisions, and I will set the gravity to downwards -5. Right. So here I have my transform nodes, which are important to have the effect properly follow the in-game instances. If I disable that, everything spawns at the origin, and yeah, I don't want that. So in the velocity, I will wire in an upward shooting velocity, and I'll add to that a small random sphere, something like this, right? And I will also expose this and randomize the upward shooting velocity. Right. So here I have my basic rig, and now I will set the color by building an RGBA value, where in the alpha I'll wire a random value between 0 and 1. So that's my basic rig, similar to what I had in Niagara and PopcornFX V1, and now I need to make this value, this alpha value, progressively reach 0. So I can either use the timer node, as I showed earlier. Same thing here as in V1, I need to saturate it to clamp the alpha, and here in the timer I just put 0.8 and I will get the exact same result as before. So we don't want to use the timer node, we want to do this load and storage frame by hand. So what I would want to be able to write would just be multiply the dt by 0.8 and have basically the same thing as here, except I need that load and store, because here it obviously doesn't work. The particles aren't fading anymore, and this is because every frame the value I assign to the alpha is the initial random minus the dt for that frame, but that's it. Every frame it will just be the initial random minus the dt of this frame, and it will never accumulate. So to cut the chase, I'll just tell you how to do it. You just have to wire in a discretization node here, and magically it works. So what does this node do? To see that, to explain that rather, I will open the other simpler effect that actually displays the values. So here I will do same as before. Right, so here I have my setup. Whenever I reset, I get a different random value. And so what the discretization node does is that it basically does a store. So you can view it as a store node, more or less. If I switch back to the exec rate view, what happens here is that the graph compiler, when it finds a discretization node, will walk back the graph until it finds a spawn to evolve transition, and this will tell it, oh, this is the place I need to store. So here, if I create a pass-through and I set it to evolve, this will be a bit clearer. So the spawn to evolve transition is right there. Actually, this should be displayed by the node graph editor here as a small yellow line that goes out, but it would be clearer, but it doesn't do it. So I just use a pass-through there to make it more explicit. So what happens here on the first frame, actually let me do something easier. I'll ditch the rand for the time being. So here on the first frame, this value starts at 0. Then it gets loaded by the evolve nodes, because each frame, when the evolve nodes run, they need to load the initial frame, so the initial value stored at the spawn stage. So there is a storage anyway there. So on the first frame, this value gets loaded. Then we subtract the DT, and then we enter the discretization node, which does a store back to this initial storage. On the next frame, now instead of 0, I'd have 0 minus 0.03 or something. Then we subtract the DT again, and we now have minus 0.06 or something, which gets stored, which gets loaded back on the next frame, etc., etc. So you can see this yellow line, this yellow path, as basically the frame loop. So this is a discretized section of the graph, and every frame it will loop, reload the value stored on the previous frame, etc., etc., etc. And you get your timer, where here the decreasing timer. So even though you can't reference it, note that we do obviously have some storage there. So that's all the storage from this particle. A good deal of it is due to the draw screen number. But you can see that these are basically the internally determined particle fields or particle attributes that we saw in the two other engines. So for example, with this fountain, you get these and you kind of find the same stuff as what you had, what you saw previously in V1 and Niagara, but you can't reference them directly. These are all internally generated and optimized. So I don't really like using pass-throughs at the beginning of my discretization paths. You don't need to add any specific nodes there, but it's a little bit less clear, I think, what's happening. So usually what I end up doing is just drop another discretization node. This is always evolve, so it has the same effect of adding a pass-through at evolve there, except it kind of encloses the discretized section in a bit a cleaner way, I think. And if you look at the physics and collisions node and any node that does discretization internally, you will see this exact same pattern. So here it starts with a discretization node, it ends with a discretization node. So I said you could see that as a store node, but it's not strictly speaking a store node. The discretization node will cause a store to happen, but it's only the last discretization node in the discretized path that will cause a store. So that's why they have this kind of waypoint icon. They just say, oh, whatever wire this is on the discretized path. So this allows you to specify where the discretized path is, basically, and the consequence of that is that the graph compiler will insert a store at the end of the path and a load at the beginning of the path, but it's not strictly speaking a store node. That's why we don't call it a store node. So that's it for this video. I hope you enjoyed it and it was useful. It will be the first of a series of at least 3, I hope, where I will give some more practical examples of what to do with discretization. Some of the core lib nodes use discretization internally, such as the physics or collision or the timer node. So this allows you to not have to worry about this stuff most of the time, but sometime you won't have a choice but use it. So yeah, those upcoming videos will cover that. Thanks for watching and see you next time.